Georges Lemaitre's models of an expanding universe were originally based upon Albert Einstein's theories of general relativity, which he had formulated some 20 years earlier. But when Einstein heard about this radical new theory, he was uncomfortable. He declared that Lemaitre's maths were sound, but his physics was atrocious. The problem was, once again, the implication that an expanding universe must have had a beginning. But here it wasn't the theological arguments that cast it into doubt, rather the fact that the physics of the time had no explanation for how such a thing could happen, or what it even looked like. Lemaitre extrapolated the universe back to what he describes as the primeval atom, which contained within it the potential for the entire immeasurable universe. We can trace the beginning of time and space back to this single point, but as for what it looked like, or how it worked, even now, physicists aren't sure. When all the stuff of the universe is compressed into an increasingly smaller space, the laws of physics dictate that the density will increase, and so will the temperature. We have a good idea of what happens to matter under these kinds of conditions, thanks to small-scale experiments in gigantic particle accelerators. But our experiments and our understanding can only go so far. After that, things become unclear. Beyond the realm of particles and subatomic quarks and their mysterious companions is a compressed universe of pure energy, where weirdness rules. The fundamental laws of physics which govern everything we see and experience break down. It becomes harder and harder to predict how this hyperdense and hyperhot primeval universe worked. How small could it really get? What makes it begin to expand? In the last few decades, theoretical physicists have grappled with tentative theories. One that reigned for a long time is that the cosmos began as a gravitational singularity, a single one-dimensional point from which all of time and space were birthed. This is not dissimilar to the singularity at the center of black holes, like the one that lurks at the center of our galaxy. The singularity is a point that is so immeasurably dense that the gravitational pull from it reaches infinity. In the case of black holes, the gravity is so strong that light cannot escape. But a singularity at the beginning of the universe would have no light to consume, as it already contained everything there was to contain. If the universe today is infinite in extent, then the infinitely small singularity would have a density and temperature that would also extend to infinity. Concepts of infinity stretch our minds to breaking point, and that's not the only problem with gravitational singularity as a starting point. If, at the moment of its beginning, the cosmos had been an arbitrarily dense and hot point, then scientists believe the universe that resulted from it would have looked very different from the one in which we find ourselves. There should be huge fluctuations in temperature and density from one end of the cosmos to another. And there aren't. There should be ultra-high temperature relics of the infinitely high temperature state. But there aren't. Space itself should be more lumpy. But it isn't. In fact, the universe is remarkably uniform when looked at as a whole. The fluctuations in temperature and density that we see average out, and you would struggle to pinpoint yourself in space based on these kinds of features alone. Cosmologists go so far as to say that it is smooth. And the chances of a singularity creating a smooth universe are infinitely small. But there is another option. It may have all begun with a period known as inflation. During this inflationary period, right at the earliest moments of the cosmos, space expanded exponentially, doubling in size from one moment to the next. Things that increase exponentially get very big, very fast, and so this cosmic inflation was sufficient to put the bang into the Big Bang itself, expanding much faster than even the speed of light. It was enough to stretch the universe flat, and to make it uniform all over, which is precisely what we see today. According to the theory, the universe was imbued with energy, which caused the exponential expansion. When the exponential expansion ended, although we don't know why it ended, the energy inherent to the universe is converted into matter and radiation, marking the beginning of time and space as we understand it. The features of the modern universe only allow us to see the final decillionth of a second's worth of this inflation. That's 1/10 to the power 33, during which time physics made a little more sense, but we still don't know how long the inflationary period lasted. Could the inflation itself have started with a singularity? Logic says no. If exponential expansion means doubling in size, then running that in reverse, we see the universe shrink to half its size, then a quarter, an eighth, a 16th, and so on. The fractions become vanishingly small, but they never reach zero. From a purely mathematical point of view, a singularity of zero size is an impossibility. So, right now, we don't have the tools to understand or describe inflation any further back. We may never understand it. The origins of cosmic inflation extend back into the fog of pre-time, beyond the reach of science and into the realm of pure speculation. Thus, the Big Bang is perhaps not the beginning of the universe at all, but rather the line drawn in the cosmic sand, marking the limits of our own understanding. Not a beginning, but a history whose opening paragraph may be several pages in, but is the first to make any real sense. And yet, if we really stretch our minds to the limit of our comprehension, the extreme edges of theoretical physics may give us the tools to break through that fog.